Hello students. Although there are a wide variety of freefall problems, that is, problems where objects are being acted on by the force of gravity, when you're solving freefall problems, they will typically fall into one of three different categories. And this is a sample of the first of those three categories. How far does an object fall in a certain period of time? As with all of our problem solving, we read the problem carefully and we make note of the information that we have, and we make note of the information that we're looking for. A stone is dropped into a deep well and is heard to hit the water 3.41 seconds after being dropped. Determine the depth of the well. So that value, 3.41 seconds, is obviously the time. So we'll make note of that. And the last sentence, determine the depth of the well, tells us that we're trying to find the distance that the stone falls before it hits the water. Now, with just that piece of information, the time, we can't use any of the equations that we have. Time appears in the first equation, in the third equation, and in the last equation, but we don't have enough information to solve for delta x. And that's because there are some things that you can assume in a freefall problem that you can't assume in some of our other problem solving. So we actually have more information than just the information that's listed. Since all objects that are only being acted on by the force of gravity accelerate with the same acceleration, then we can make note of that acceleration. It's assumed to be true in this problem. So the acceleration caused by gravity is 9.81 meters per second squared. We're going to take that as a positive value in this problem, which means that we're taking downward to be the positive direction. Now, it might seem more conventional to take up as the positive direction and down as the negative direction, and in some problems we might do that. But in this problem, the object is only moving down, so it makes sense to take the direction of motion as the positive direction. And when the value of A is equal to 9.81 meters per second squared, it means that the object will speed up with that acceleration as it moves toward the Earth. And that's what happens when an object falls. It speeds up. If you were to toss the object upward, it would slow down as it moved away from the Earth. It would speed up as it moved toward the Earth. Given that all objects fall with this same acceleration, if they're falling on Earth, that means that we have this additional piece of information. So we also have A, and so I can check that off in all of our equations. That's still not enough information. We can't use any of these equations. There are too many variables that are unknown, so we can't solve for delta x at this point. And what we need to do is take into account this additional piece of information. By using this phrase, a stone is dropped, it's implied that the initial velocity of the stone is 0 meters per second. When you drop something, you hold it in your hand so it's not moving, and then you let it go. And then it begins moving, it begins accelerating, moving faster and faster as it falls toward the Earth. In most of our freefall problems, the initial velocity will be 0 when the object is falling downward and speeding up as it travels toward the Earth. You can throw an object downward. You can give it a speed other than 0 by applying some force to it in addition to the force of gravity as you throw it downward. But that's not what's happening here, and that language wouldn't be used. So by using the language a stone is dropped, it's implied that the initial velocity of the stone is 0. So it turns out that we had two additional pieces of information that were not explicitly stated in the problem. That is, the acceleration is 9.81 meters per second squared. We're assuming this object is falling on Earth. and the initial velocity of the object is 0 because it's being dropped and allowed to fall downward. It's not being forced or thrown downward with a higher initial speed. So if I know the initial velocity, I can check that off as well. And so now it's time to look at the equations and determine which ones it's possible to use and which one it would be best to use for this particular problem. So it's not possible to use the first equation because I don't know the V average or the delta x. So I can't use that equation to find delta x because I don't know V average. And it's not possible to use the second equation because I don't know V average or VF. It is possible to use the third equation. I do have VI and A and T, and so I can use that equation to find VF. And that's going to be one of our problem types. How do you find the speed of the object right before it hits the ground or after it falls for a certain amount of time? But we weren't asked to find the final velocity, so it's possible to use that equation, but that's not the equation that's best for this particular problem. We can't use the fourth equation because we don't have VF, and so we can't find delta x that way. We can use the last equation, the fifth equation, which is solved for delta x, and so that's a very convenient equation to use in this particular type of problem. Another thing that makes it a convenient equation to use is that the VI value is equal to 0. And so when we use that equation, this part of the equation is actually going to be equal to 0 because when VI is 0, since anything times 0 is 0, VI times T will be 0. And so that part of the equation will be equal to 0, and it will be a simpler equation to solve. So this is the equation that we want to use. Delta x is equal to the initial velocity times the time plus 1/2 the acceleration multiplied by time squared. So the initial velocity is equal to 0 meters per second. The time is 3.41 seconds. We'll add on half of 9.81 meters per second squared multiplied by 3.41 seconds squared. Another thing to note when you're solving these problems, this entire term is not squared. It's only the time that gets squared. So it's not 1/2 AT quantity squared. All right? So you're not going to multiply 1/2 times A times T and then square that whole thing. You're going to multiply 1/2 times A times the value of T itself squared. Okay, so we're not going to square that entire term. Okay, so as we've already said, 0 times the time, whatever the time is going to be equal to 0. And now we'll do 1/2 times 9.81 times 3.41 squared. So 0.5 times 9.81 times 3.41 squared. And it's only the 3.41 that gets squared. Again, it's not the whole entire product of 1/2 times 9.81 times 3.41. That's equal to 57. Since the value I was given for the time, 3.41, has 3 significant figures, and the acceleration, 9.81, has 3 significant figures, I can write my value down to 3 significant figures. So I'm going to write 57.0. The next number is a 3, so I'll keep that a 0 instead of rounding it up. Notice that when the time is squared, the units on the time, seconds, also get squared. So those seconds squared will cancel the seconds squared that are in the denominator of the acceleration, and our units will be in meters. So 0 meters plus 57 meters is equal to 57 meters. If it takes 3.41 seconds for you to hear the stone hitting the water, then the stone has fallen 57 meters. All right, that's type 1, finding out how far something falls if you know how long it takes.